Good morning, everyone. It's my honor to share our research. So, a brief introduction about myself again. My name is Zhao, and currently work as an instructor at Marquette University, Wisconsin, Milwaukee. So, another author of this research is my advisor during my PhD. He's here, Dr. Wang, associate professor at Marquette. So, our study is about the modal uncertainty in reliability analysis of the FRP-to-Concrete bond with a grooves method. Today I will give a brief introduction about the grooving method, how this method improves the bond efficiency between the FRP and concrete, and what different patterns we have, and how does those patterns work. And then, okay, thank you. Because our research is focusing on the reliability model, so I will give a brief introduction about the whole picture of the reliability, and move on to the modal factor, and in practice, how we find those modal factors, and the uncertainty from the modal factor. So, external bonding of FRP composite is very popular techniques recently, and to strengthen or repair concrete structure. So with this method, actually, we can ensure the safety of the structure, especially the concrete structure, through its lifespan. We have a lot of good reason to use this technique, like the good mechanical property, corrosion resistance, and construction convenience, but definitely we have some challenges to use this technique. So the big issue is actually the earlier debonding. So actually researchers already tried different approaches. So one of them is a grooving method. So that's actually the one we will talk about. So the basic idea of the grooving method is actually we pre-cut some grooves on the surface of concrete, and then we use the epoxy fill those grooves first, and then we attach the concrete, the FRP on the concrete. So definitely we have different patterns in terms of the grooves. Like we have the transverse grooves, we have the longitudinal groove, and sometimes we may do diagonal. Actually, our group already did a little bit experimental work and finite element work about the transverse groove. And actually, Dr. Zhao and Zhao group did a lot of research about that. So actually more focusing on the longitudinal. But all those patterns works pretty good. So here is some experimental results and finite element setup for transverse groove case. That's actually what we already done. So based on the left figure, see with the grooving case, definitely can significantly improve the ultimate bond strength. Actually can improve the bond strength double it. So the mechanism idea of how the transverse groove improve the bond efficiency is actually once the epoxy fill the groove, and those epoxy ribs will provide some kind of like the interclocking, and then improve the bond efficiency. So here is some work from the Dr. Zhao group. So that's regarding the longitudinal groove. So from the figure shows same thing, same conclusion. The grooving method significantly improve the bond efficiency. So all the solid line is with the groove, and all the dashed line is without groove. So grooving method significantly shows the potential to improve the bond efficiency, but to use this method in the real world construction project, it still have some challenge. So due to a lack of the reliability analysis. So we don't know if that's safe or not. We do not have the standards. We don't know how to set up standard for that. So our group already did a little bit work about the reliability analysis. So today's research is a part of that. So our work is just focusing on the longitudinal groove for two reasons. The first reason is like I mentioned from the external work, actually the longitudinal groove already showed the good potential to prove the bond efficiency. And another reason is once we do the reliability analysis, we need a large amount of data. So if we do not have enough data, so no idea to do the reliability. So actually currently, the longitudinal groove can provide more data. So definitely if we have other data coming, like from the transverse groove, like the diagonal groove, we can just copy this method and then to do the reliability analysis. So that's an overview idea of the reliability analysis. So to do the reliability analysis, the first thing is we need identify the uncertainty. So usually in terms of structural reliability analysis, the uncertainty coming from three parts. The one part is modal factor uncertainty. So it is from how we derive the formula to predict the bond strength or other strengths. Another part is from the modeling parameters, like the stiffness of FRP, the concrete compressive strength, and some parameters regarding the groove, like the depth of groove, the width of grooves, or maybe in terms of transverse groove, we need to consider the numbers of groove. So the last part is definitely from the load, dead load, lab load. So once we identify the statistical characteristics of those values in terms of the mean, the coefficient of the variance, or the distribution type, and then actually we can move on to setting up the limit state function. That's actually where the modal factor occurs. So modal factor times predict bond strength, that's actually from the formula, and minus load. So set up that red equal to 0, that's actually our design point. And then we need to set up the standard, like higher than which value is safe, lower than which value is not safe. So that's actually the reliability index. So for most concrete design, that value is 3.5 or maybe higher, 3.8. So we just keep continuing input the value till we get the satisfied the values, and then we close the loop. So that's a basic idea of the reliability analysis. Actually, so the uncertainty group number 2 and number 3, the modeling parameters and loading, researchers already did a lot work about that. So actually we can directly get the data from the literature. But the first part, the modal factor, not too much research group focus on that. That's actually what we will do. So the modal factor is defined as a ratio between the measured value, that's from the experimental work, and the corresponding predict value, that's from the derivation, how we predict the value. So definitely there's some uncertainty for that value. So if we plot the test value versus the calculated value, so actually we can see how these data distributed along the 45-degree line. And our job is to find the statistical parameters for that value, the mean, COE, and the distribution type. So here are the characterized steps to find these values. So in total, we have 4 steps. Number 1 is we need to choose a proper prediction model, and then we need to collect enough data, and then sometimes we need to do the systematic dependency check, and then we just feed in and find the COV, mean, and the proper distribution type. So I will introduce that one by one. So first, prediction model. So because Dr. Hajjad group already derived that prediction model for us, So for the longitudinal groove, we can directly use that. And in case we do not have that, actually we have two methods to get the prediction model. One is a regression, one is a theoretical derivation. But anyhow, we can get that. So based on this empirical model, actually the bond strength is highly depends on 5 input parameters. Number 1 is the stiffness of FRP. Number 2 is the strength of concrete. And number 3, the head of the groove. Number 4 is the width of groove. And the last one is bond width, actually the bonding area. And we will collect the data for all those 5 key inputs. So in this study, we collect 136 data. That's actually all we can find currently. And definitely in terms of reliability analysis, if we have more data, and our analysis will be more accurate. So the range of the FRP stiffness is from 12.9 to 78.2 kilonewton per millimeter. And the width of FRP is actually from 30 to 60 millimeter. And the concrete strength is actually from the 22.7 to 48.2 megapound. Groove height and the groove width are both from 5 to 10 millimeters. That's the summarized database. So the ideal case is if all those input data are perfectly random, and then we can directly fit that. But usually they are not random. Actually, there are some systematic dependency, especially once experimental work were conducted by different people, different group, different size of FRP, different concrete. And definitely we have some dependency, and we cannot directly fit in those value. So we need eliminate that systematic dependency. So that's a very important part. So to do that, actually we decompose the model factor into 2 parts. The first one is actually where the dependency comes from. That's we call that systematic part, F. And definitely another part left. That's actually the one we want, residual part. That's totally perfectly random part. So to find the systematic part, actually, we use a multi-nonlinear regression to fit it. And we use a powerful function. Actually, we have different options. We can use different exponential or others to fit it. Actually, before we're fitting that or try to find a dependency, we need to check the correlation. So here we check the correlation between the input parameters and the prediction value. The left figure is a heat map between the inputs and the prediction. So from this figure, actually, the darker color tells us more correlation. The lighter tells us no too much correlation. For example, the prediction to prediction, definitely self to self, is the more correlation. And then the lighter one, like the prediction to the width of the prediction to the concrete strength is actually pretty lighter, so then not too much correlation. So actually we do the Pearson check for all the input versus the prediction. And then the good thing is for our study, because all the p-value is higher than 5%, that means there's no significant correlation. But this step is necessary. We cannot assume it's always true. So the routine is we need to check that. And then if we go back to here, and all the AI 1, 2, 5 will be 0. And then give us F is 1, but not always. So once we eliminate the systematic dependency, actually we can use the fitting, we can use a potential curve or distribution to fit the perfectly random part. So usually regarding the structural analysis, we have 4 pretty good candidate distribution. One is extreme, one is Weibo, and one is normal, one is lognormal. Actually, we use all those 4, try to fit them, and definitely that's a fitting results for the extreme. That's fitting results for Weibo. That's fitting for normal and for lognormal. Sometimes the results is obviously, like our study, lognormal works best. But sometimes you cannot directly use your eye to find which one fits best, right? So we need to evaluate which one works best. So we can plot the contile plot, and then the linear line is actually a theoretical data line. So everyone just compare with that. So 4 candidates compare that. The closer, the better. And definitely the lognormal is best. And also we can do the most likelihood fit check. And we did that, and the results tell us the same conclusion. And the lognormal fits best. And then so far we got everything we need. That's actually the statistical parameters for modal factor. So we got the mean. We got the, regarding the lognormal, the mean is 1.01164. The variance is 0.0093, and the lognormal works best. So those three are very important regarding the whole reliability analysis. It does affect a lot. So in conclusion, our study is more like a case study, and we were focusing on the longitudinal groove to improve the bond efficiency between FRP and concrete. So we find the corresponding residual modal factor, so which distribution works best, lognormal, corresponding mean 1.01, and the variance is 0.0093. And not only for this case study, actually our work can definitely use to other study. So we provide a framework to calculate the modal factor uncertainty. So just follow the framework step by step, and then definitely we can get everything we want. So definitely this framework can be used to other uncertainty analysis regarding the reliability analysis. So that's actually our future work. So in future we will integrate this development model and into the reliability assessment. And definitely the more modal factor uncertainty we consider, the more accurate reliability analysis we will get. And that's actually the future work we will do. Yeah, thank you.